Supersonic Speed with JVM Args. And I'm going to go through a little bit of context in a couple different ways before we get into the meat of the JVM Args, but that's just to set the stage for what this is. My name is Jason Pearson. I'm a senior staff engineer, formerly Hinge. And first, about me, just a little bit. This is where I am. This is what it looks like right now. It's just ice and snow forever, as far as you can see. At least it will be very soon. And when it's not ice and snow, it looks like this. We're on Lake Superior and just water everywhere. And I'm up in Minnesota, a little bit north of Texas. My CI experience started in 2011 when I ran afoul of a build system that I didn't understand, and then spent the next decade or so figuring that out. I built Android at Hinge. I went from solo dev to 24 Android engineers. I also spent years in backend and full stack across different companies. This is generally going to be the agenda, just a little bit of build context about the project that I'm referring to. Then we're going to get into the JVM Args, explaining them, and then using them to make the build as fast as possible. How much faster? This is the goal. 3-minute unit tests, 9 minutes to release, 1 minute for UI. The context for the project that I'm talking about, it had 400 modules, 290,000 lines of code, 24 active contributors. We were using Dagger Hilt with capped. It has since already migrated completely to KSP in the last 2 months, and mostly Gradle Kotlin scripts. So from the point of view of someone who's publishing an app and doesn't have it automated and it's on their laptop, you have an AAB file you throw onto the Google Play console, and it spits out an APKs, and then people download it, and you have this wonderful problem of lots of people wanting more features. We're not going to talk about that problem. We're going to talk about the problem where you automate build features on your laptop, and then you hire more devs, and then you want things to move faster because everyone's asking for it to move faster because you automated it, but the thing that everyone is asking is, why is CI taking so long? So it's taking so long because of all the things that you're doing in CI. Your automated building and publishing, you automated tests, you automated security, all of that takes time. Now, how do we get back to a reasonable amount of time? It's always going to take some time. Generally, you want to do as much caching as possible. That is across every single CI pipeline that anyone ever makes. You want to utilize the JVM args that you have because we're talking about a JVM build, and you want to utilize shadow jobs in a variety of different ways. Generally, for an Android build, this looks very reasonable. Most teams would be very, very happy for this, but we want to get here. So how do we get to it? We're going to focus on the unit test portion, and for the rest of the talk, what I'm going to do is have this up on the slides, and every once in a while when we make progress, I'm going to show you how we knock it down and by how much. Generally, we were starting through a 6-month period of work around this amount. Control is without any optimizations whatsoever, just so you can refer back to how far we've gone. Partial cache hit is when we at least get a Gradle wrapper cache hit and maybe nothing else. Cache hit core changes, we've changed some core file, everything's going to recompile. Cache hit leaf changes, some feature has changed in the project. So the first thing that we're going to talk about is just caching dependencies, because it's the easiest thing and one of the biggest wins right off the bat. The Gradle cache for an Android Gradle build system is made up of the build cache, where you're executing, the dependency cache, where you have your AAR and jar artifacts, the script cache, which is all the Gradle Kotlin script, and the configuration cache, the lovely thing that almost never works, but when it works, it's lovely. So I'm going to keep referring to these different build caches over time, and we're going to start with a build that's right out of the box. Nothing has remote support. Local support means that I can reuse the cache on my local laptop, but not on CI where I want to. we're going to focus on the dependency and the script cache first, because that's the easiest thing to get working. If you look in your Gradle user home directory, you'd see something like this, where you see a .gradle folder, got caches folder, and different versions, build cache jars, journal, modules, transforms. The things that we care about is modules 2. That's more or less a dependency cache. Some of the documentation mentions that jars 9 is also required or also part of the dependency cache, but in practice, I don't see the win of caching it. Purely for dependency caching. Script cache is over here, Gradle generated jars and Kotlin DSL. Fun thing to note, I have a colleague that has been able to cache this separately from the rest of the build, and therefore reuse this across many different jobs. Not going to get into this talk, just noting that it's possible. So straight out of the box, if you write a YAML description of the different things you want to cache, if you just did this, and you would have remote support on CI for your dependency caches. You wouldn't have to re-download dependencies every single time and re-resolve them, as long as they haven't changed build to build. That saves a decent amount of time. How much? About a fourth in the build that I'm talking about. So that little purple that got added to the partial cache hit, that is indicative of we had to spend some time saving the cache, and that also allowed us to save time on all 3 of those builds. Obviously in control, we haven't changed anything there, so it remains the same. Next thing, before we get into anything with JVM Args, there are some things with Gradle builds that allow JVM Args to succeed a lot better. So prioritizing those quick one-liner wins, and the fact that none of these things are defaults out of the box if you like open Android Studio and make a new project. Surprisingly, these 2 things are not default in a new Android Studio project. They should be, because they're really important and they're very foundational to everything that we do. So enabling Gradle caching, that allows you to reuse the build cache, and Gradle parallel, that allows you to build modules in parallel. All the advice about modularization would be completely wasted if you didn't enable both of these things. If you're on Kotlin 1.7, you should really enable this flag about use class path snapshot for incremental compilation with Kotlin. If you're not on this version and you're on a really old legacy app that needs to update, you should call this out to your team and say, hey, this is a reason to update. There's actually a beneficial win here that we can get. Only if you're still on capped, you should enable this. Hopefully your team can migrate off of capped as soon as possible. If you're still on it, enabling this flag does have some benefits. Another thing is enabling the build config as bytecode. This essentially stops generating Java stubs, and if you're not generating Java stubs, there's a whole Java build step that doesn't need to happen, and also cache results and other things. So if this is the last thing in your code base that's generating Java, it'd be great to enable this. If you're still using Dagger with capped and generating Java stubs there, this is pointless to enable or not. It does work in most recent Android Studio versions. Another thing you can do is disable generating build config for most of your modules by default. You probably only really need one to hook into whether or not you're a debug app. You do not need a build config per module, especially if you're talking about a 400 module project like ours. Disabling this did save some time, it was a couple seconds overall, but it's a one-line change, so why not? Again, R8 Max workers, this is an experimental flag that the Android Gradle plugin has rolled out, and the benefits are still not that great or not that significant, but I think enabling this and making sure that your project runs with it so that when we are able to realize those benefits is worthwhile. So just overall, if you were just look at your Gradle build file, or Gradle properties file, and see if these things are there. Try them out. So that's Gradle properties. And then if you wanted to know where I find these, a really good resource is just looking at the Android X repo and other open source projects. That alone didn't save much, but it was all one-line changes, and therefore it's pretty great in terms of investment or level of effort for return. Next thing is caching the build steps. I promise we are going to get to the JVM Args. These things are relevant and tied to each other. We're going to focus on the Gradle build cache and getting its local support to be remote on CI. Very first thing to do is look at the Gradle Enterprise build validation scripts. It's important to note that you can't really use these things unless you have Gradle Enterprise, the paid product. So that's a caveat, but assuming you do, these are very important to run so that you can understand whether and where your various build tasks are cacheable or not. They help you find and identify regressions and potential issues and areas of investment in your Gradle build pipeline. You generally want to modularize your code base, but this is very vague advice across the industry. Specifically, you want to reduce the number of inputs per task and make them more stable. So a smaller module is generally better. I really recommend watching Siggy's talk from DroidCon SF about modularization and graph theory. He talks about betweenness centrality and measuring that in relation to modularization efforts and how to target modules as a result. From what I can see of his talk, he's really onto something, because the intuitive thoughts of engineers looking at a module as to whether or not they should target it for modularization and breaking it apart. This is a measurable metric that identifies that. And also, if you're measuring it over time, you can see whether it goes down and whether that actually correlates with build times. From what I can see of his research, it does, and it'd be great if more organizations try to adopt this and publish their results. Lastly, just using Gradle build scans to observe performance. Sometimes Gradle build scans can be frustrating because of the lack of information that they reveal. However, not ignoring them completely leaves out a world of information that you could obtain. For instance, knowing that your team is using old JDKs or old settings that don't make sense or can't reuse the cache that you're trying to establish for everybody. And about reusing the cache across the team, it's possible to use Gradle Remote Cache, and you should just do it. If you're limited to on the amount of money that you can spend on CI pipelines, following the link to the cache build cache node, it's a free project that you can just run yourself. Recommend 90 days and 300 gigabytes and using the validation scripts. Again, that's the paid path. Most local and CI runs will benefit from build cache hits. But if you have budget, and it is definitely worth it out of any investment that you could put into CI, going with Develocity, the new Gradle Enterprise branding, it provides support for features beyond the remote cache. Specifically, it helps figure out failures across teams, cache misses and performance issues, and really looking forward to using test prediction myself. I've talked to colleagues that have real world experience with this, of anywhere from 40 to 70% test avoidance, which is pretty huge in most commit-based builds. So that would be a great win. And going through all those steps, we would get to remote support for that. And that gets you this much of a win in terms of our build time. So finally get into the meat of JVM Args with this talk. First is it worth to use the latest JDK? And the answer is yes, please, 19 plus. Anything less than that is a little outdated for today. because 19 gets you quite a big win. 20 and 21 make incremental improvements to the G1GC algorithm, and I haven't been on a project since I've been doing this research where I could test the differences at that scale. Testing it on a test project is incredibly insignificant and doesn't make a difference. So if you're on a starter or a small project that's like 50 modules or less, you wouldn't notice a difference on these things. If you are on a hundreds of modules project, you would notice a difference. And going from JDK 11 to 19 on the project that I'm referring to, just that alone made a pretty significant difference of like 20% in terms of build time across everything. So that also brings up the question of upgrading tooling, and will JDK 19 work on our project? Well, will version X of any dependency work on our project? And that's kind of a hard question to answer without doing something like shadow jobs, or at least my interpretation of it. I read the article that Zach Swears put out about shadow jobs and how they were using it to look at different versions of tooling and how it would integrate with their projects, whether it was the latest JDK, the latest AGP, whatever. And not only did we run nightly checks against your project with the latest snapshots, new versions like he recommended, but then we also did some JVM argument tuning using this. We parameterized our entire builds and looked at what those different arguments did. And this is the result of that research. Disclaimer, I am not accountable for any of these settings. They are incredibly, wildly different on every single project, on every single different machine, and your results may be incredibly different than mine, and this is not a PhD peer-reviewed research paper. So with that disclaimer, just want to go into JVM Args and start with the garbage collection algo trade-off. Each JVM GC algorithm makes a choice about what they optimize for and how much. There's throughput, latency, and footprint. And the throughput is about how fast it goes transactions per second. Latency is time spent in GC pauses, what the algorithm would allow time for. And the footprint is just how much memory it's going to use, essentially. And you should think of these things as points on a triangle. They're trade-offs that the algorithms make and how they're programmed. Generally, the ones that you're going to think of for an Android build, and most Gradle builds for that matter, are parallel and G1. And this is where they sit on that triangle. They're fairly close to the throughput end of the spectrum, where G1GC pulls back a little bit on throughput and more towards latency and footprint. It makes some accommodations to try to reduce the amount of memory and reduce the time spent in GC pauses for overall performance across most builds. So what does that really mean? Parallel optimizes for speed, maximum footprint, might have longer GC pauses. There's a plugin called Gradle Docker, and it still recommends today that parallel is what should be used across all Gradle builds. And it will by default error out if you do have anything else selected. G1GC balances throughput, has lower footprint, shorter GC pauses. It's probably the safe bet to be stable and fastest for most projects, especially because the JDK 20 and 21 improvements made significant memory wins and latency wins. Overall opened up more memory in native memory to be used by your build instead of by the overhead process to manage garbage collection and manage keeping track of everything inside your build. Sorry, excuse me. So what else is going inside your build? All that overhead. There's the Gradle and Kotlin daemons, and in order to tell them what they should use, we need to learn how to do that. And one of those things is the Kotlin JVM arguments. The old way of doing this is through Kotlin-Daemon JVM options. And this is old and bad for a variety of reasons and has lots of disclaimers, especially this weird one. The arguments that come after a space will be used for the Gradle daemon, not for the Kotlin daemon. It's kind of weird. I'll get back to that. And lots of other disclaimers about the different versions that it won't work on. It does call out that there's this new option, Kotlin daemon JVM Args. It's very simple, has no disclaimers on the documentation. It probably should, because I ran into this. If you use spaces at the beginning, it will cause all arguments to be ignored if you're doing JVM performance testing and seeing no difference in your results, and you see spaces at the beginning, this is why. The JVM heap size for both the Gradle and Kotlin daemons are really important to keep in mind. The max is the amount of memory that it takes to compile your biggest task. And it's reused across compiling all your modules. For most projects, this is going to be your main app or your modules minification step, or maybe Android lint, or maybe Android unit test, because whenever you fork a process with unit tests, that can be that could end up with a separate limit or an increased limit. I'm actually not sure off the top of my head right now. The min is somewhere between, should be between 80 and 100% of the max, because the heap will only grow every time you get a GC event. So if you start at 1 gigabyte and you hit that, it will grow by a certain amount per the algorithm that you're running. If you know that eventually your build is going to grow to 16 gigabytes or 12 gigabytes or 4 gigabytes, why not just set the minimum to that amount? And then you don't have to deal with GC pauses early on in your build. And I did mention earlier on in the talk that the various Gradle options and modularization, all of that stuff is related to the JVM arguments. And specifically, this is how. JVM heap size and modularization are related because any given module, any given task, you need to have a certain amount of heap size to complete a given task. And if you're running with parallelization, you want your workers to be able to, you want as many workers as you can to spin up in parallel. If a given task takes a certain amount of heap, and I was talking to Inaki about this, he was telling me that the Gradle worker will, Gradle will not spin up new workers if it cannot satisfy the requirements for JVM heap, JVM arguments in general. So if you have a single module, let's say it's home, and it's a gigantic module, hundreds and hundreds of thousands of lines of code, takes so many gigabytes of memory to complete, then you have a bottleneck in a variety of different ways that really needs to be teased apart in order to proceed with modularization of your build. This does seem to track with what Siggy was talking about in terms of between essentiality, but I just need more time and more research to prove that. Another couple things in terms of the overhead of JVM that it manages under the hood. Metaspace is an interesting one, especially with Gradle's history of how it's been managing it over the years. There's inside of Metaspace, there's your max metaspace, the overall amount, and the compressed class space size, which defaults to 1 gigabyte. And this is what it looks like. The blue, the bottom part with the blue and red is your compressed class space size. That's always going to be 1 gigabyte. And then the non-class space list is variable. It can grow unbounded by default with the JVM. Interesting thing about these things is that it will only be enabled and only allowed on heaps under 32 gigabytes. It will default to on under 30, but it is allowed up to 32. That's because of memory limitations and the fact that it uses 4 fewer bytes, which is faster. So that compressed class space size is only available through compressed class pointers, and that's available if compressed oops is on, and that's about the 32 gig limit. So what if we turned it off on our project? We just tried it and we saw that it ran slower, and that's because of that 4 fewer bytes. It's faster to run on an access memory with a smaller index. That makes sense. And what we found through our research was that compressed oops and unlimited max metaspace is going to be better for the majority of Android projects. Gradle by default, if you don't set any JVM Args, it limits max metaspace size to 256 megabytes, which doesn't really make sense with the compressed class space size being 1 gigabyte. And I'm also not surprised that as a result, there are issues both on the Gradle issue tracker around running out of metaspace. So at least on the most recent versions of Gradle, this doesn't seem to be necessary anymore. And I'd really like to work with the Gradle engineers to push for like why this needs to continue to be a default, and only a default when developers don't set a setting. That seems crazy because it's a foot gun waiting to happen. The second that you run into scaling your build, you try to configure it, and then everything changes out from under you. And what we found was setting not max metaspace, but metaspace, the starting amount of metaspace. Think of it as like minimum metaspace, like minimum heap size, to 1 gigabyte, helps avoid early metaspace related garbage collection events. If you want to measure metaspace in your build, how much are you using? What does it look like? There's this handy command that you can point at any given Java process and look at the metaspace results. And I'm going to definitely in the notes point out some articles about what you can do to there's an entire blog series explaining metaspace and this command, how to look at the results. So next on the overhead stuff is code cache, and it's where the JVM stores its bytecode compiled into compile native code. Reserve code is the maximum amount for cached bytecode. Essentially, that means as Gradle is compiling your app, it's looking at the bytecode that it compiles, and it caches it, and if it matches it later, it can reuse it. And if it runs out of space, it will fail your build, just straight out. By default, it's around 32 megabytes, and again, that runs into pauses as it needs to increase that cache size. So giving it just a larger amount sped up generally Gradle builds. And if you want to determine the only way to measure it that I can see is that you pass this as a JVM arg, print code cache, and it will print out the code cache size that you've ended up using. So if you do grow to 200 or 400 or 800 megabytes, there's no reason why you shouldn't set that reserved amount to the eventual number. You can avoid some pauses in increasing it. So instead of only setting things to be bigger and using more memory, which is what the JVM loves to do, there's this other setting called soft ref LRU policy. And it's kind of weird, especially with Gradle and CI and builds in general, because what it stands for is the number of milliseconds to hold on to soft references per megabyte of heap size, default 1000. And this is for just JVM apps in general. It's not specific to Gradle at all. So if I run a build, and let's say I give Gradle 8 GB heap, and I have the default policy, it's going to take 2 hours and 16 minutes in order to release any soft reference, not just the like some of them, but like the very first one that I happen to cache it as a soft reference. So this typically means that Gradle is not going to release any of them, the entirety of your build. Hopefully your build is less than 2 hours. If you set the policy to 10, it would take 1 minute, 22 seconds. If you set it to 1, it would take 8 seconds to release a soft reference. Now, soft references, that mechanism is meant to allow you to configure at the JVM level how long soft references are held. And it's meant to be tuned. It's not meant to just be like, hey, take the default and just live with it. For CI and build purposes, we tuned it to 1, and we saw like a 30-second improvement on our build out of all these other things. So there's no danger to holding on to this. If Gradle needs to recreate a soft reference, it will. And you can even set it to 0, although we did see a performance dip compared to 1 millisecond. So that's what we set it to. Lastly is just max workers with Gradle. This is not a JVM arg. This is just a Gradle property. And it's the number of max workers to allow, although it's related to your JVM args. If you're going to be tuning your JVM args and not max workers at all, you're going to find that you're not going to get to the optimal solution. Generally, it should be the number of performance cores, possibly 1 or 2 less, especially if this is a configuration that's shared from local developer machines. You want to have Chrome running and, I don't know, Spotify maybe. And then there's your memory allocation replacements. These are really fun because I can't possibly talk about this topic inside of a tech talk. It would take hours. But generally, memory fragmentation slows down builds. Memory fragmentation happens because the JVM allocates a certain amount of memory and says, okay, like I need this size block. I'm going to put 5 megabytes here. And then it says, oh, I need to allocate 10 megabytes. I'm going to throw that on top. Oh, I need 5 more megabytes. Throws that on top. Oh, I can take the 10 megabytes out of memory. And then you have a 10 megabyte hole. JVM says, oh, I need to allocate 15 megabytes. Where do I put that? Oh, on top. And then what happens by default is that this keeps going and you keep wasting space by default. There's certain conditions for when it does compress, but the default resolution strategy is not nearly as good as these other algorithms. And therefore they don't reclaim memory. Both JMalloc and TCmalloc do reclaim memory quite aggressively. They have different traits. JMalloc seems more naturally suited to Gradle builds, at least from the cursory research that I have done so far. And we saw no speed difference with it, but we did notice a 10% less memory usage, which then you could turn around and take that memory usage and increase your overall heap size and make your build faster that way. Yeah, what I just said about less memory pressure. So what did we actually end up picking? We ran shadow jobs on all these parameterized things. We said, hey, what worked? And then we said, okay, the GC algo for this particular code base was parallel, but I'm on the slide, I'm definitely putting it depends in case anyone screenshots it and just takes these parameters right into their code base. Everything else is generally what I would recommend for a general Android code base, whether you're a starter or getting up into scale. Definitely curious to talk with people at the end of the talk what they've experienced and if they've seen different performance based on these things. If you want to measure these things, GCMP for metaspace, print code cache for code cache, and generally you're going to have to just measure CPU and memory resource usage. There's lots of tools available. There's a Gradle profiler project. However, it's not Gradle configuration cache compliant, and therefore I don't really use it. So that's how much that took off our build times. Our execution got down to like a minute or two. That said, I'm going to deviate a little bit from JVM Args for the rest of the talk because we did that. And at the same time, what I have left to cover is related because it allows you to reclaim more resources. So Gradle configuration cache. If you wanted to try out enabling it, these are the properties that you need to set. Really recommend just looking at the Android X open source repo on GitHub for their ignore file system checks. And if you wanted to find it, you wouldn't find it in the Gradle user home directory. You would find it in your project. And you would find it under the .gradle directory in your project. And you would see configuration cache as a folder and be like, oh, I just need to cache this. Great, done. And then you realize it doesn't work. As of Gradle 8.1, encryption was added. The reason for that is because they didn't want to leak secrets from organizations' builds, whether they're public or private, open source or not, because configuration cache literally looks at everything in your environment. So their response was that configuration cache is not supported on CI. It's only for local development. We ignored that and proceeded to spend time on it. We looked at all the inputs that configuration cache used, thousands of file system entries, dozens of environment variables and other things, and we made sure that they are exactly consistent across builds. You can look at a configuration cache report whenever configuration cache is enabled but doesn't work in a directory like this. But despite everything, we continue to get the unhelpful error message that no configuration cache is available. I really puzzled over this, and I talked to Inaki at DroidCon New York, and he said that I need to cache the encryption key. And I was really confused at first because I didn't see it anywhere in the directories. So before we go any further, just caveat, this method does cache the secrets that configuration cache encryption was intending to avoid, encrypt, and like keep safe. So this method shouldn't be used, but I do have a solution at the end. So I went into Gradle's source code and I found where the configuration cache key store was, found the directory, and I was like, oh, I also found a test that says that's the error message that I should expect in a situation where that key store is not cached or rather not found. So I went digging and I found the CC key store exactly named as I expected and had a couple of other files in it. It's like, okay, I'll cache this, add it to my little YAML list, and still get the same error message. That was weird. So I looked through our CI pipelines through a whole bunch of YAML, and hopefully I get to write and read less YAML in the future. But I found this line or set of lines about cleaning the Gradle cache. And this is straight out of Gradle's own documentation about how to prepare and clean a cache. It specifically says get rid of lock and GC property files. But if you remember, there was a lock file in that configuration cache key store. So I deleted this. And then all of a sudden, it started giving me helpful error message. Oh, it could recognize the configuration cache exists. So the key store is properly there. I just need to work through these errors and figure it out. So looked at the first one about generating external plugin spec builders, had no idea what that was about. Asked my colleague, Nicholas, and he said that Gradle has a bug about inline functions. We deleted all inline functions from our group build scripts. and we added plugin descriptors to our cache list. It's growing, but it's okay. And we got another error about patterns and some failures, really unreadable blob of error text. But if you hone in on these specific pieces, it's talking about a field in file system inputs. So we know this is a file system input. And also we know that this is referring to our root project's Gradle plugin folder. This is where all of our convention plugins are. Okay, so there's some things that are either corrupted or missing. And we ran some tests. We saw that it wasn't corrupted between builds, so it must be missing. Therefore, we looked at our Gradle build plugin descriptors, and we just said we're just going to cache the whole thing. And then we cached some more things in order to get past more errors on jars 9 transforms. And we finally got the wonderful reusing configuration cache. For context, this is what our builds on Gradle Enterprise looked like on our main branch for our release build. So this is running minification, all the fun stuff. And it's up and down because there is build caching sometimes, but not all the time. And yeah, once we turn configuration cache on with this, got down to about 8 minutes for the entire process. This is our longest build in the entire system. And my coworker said, "Oh, this is great. PR is fast now." I said earlier that I had an update or a better method. So I filed an issue for a feature request to make configuration cache better and not have to cache the key store, make it more configurable, use an environment variable. And then PR was just merged yesterday for sourcing this configuration cache encryption key via environment variable. So now that's in, and TLDR, wait for Gradle 8.6 and a new GitHub Gradle build action that should be out hopefully before the end of the year. And now everything is remote supported. Hopefully you can understand and appreciate that, like this slide about the amount of time that we reduced frees up resources and therefore allows us to modify our JVM Args to be optimized for a different build as a result. So the Gradle work and configuration cache and JVM Args are completely intertwined with each other. So what did that do to our build? Well, basically those yellow areas went away completely, and we got down to 6 minutes. That's not quite 3 minutes like I promised. So let's look at that. What was left? We had some big images with Docker, some really big Git clone pulls with 400 megabytes, and minutes to save and restore those huge caches that we've now created. Originally, I spent a bunch of time trying to make this work on our old CI provider. And then recently, I've looked at GitHub Actions and seen that, A, the base images are cached much better. They're basically instantaneous. Git pulls run about 200 megabytes per second. So even with a couple hundred megs of repo, should be pretty fast. You could use treeless clones like we did in the other project, but no need to invest that if you're pulling from GitHub onto GitHub. And then cache restore and save operations, just in terms of network and file system speed, are about 2 to 5 times faster, and therefore why optimize something that's just stupid fast? So all of this goes basically 0, and we did all the things. We cached everything that we possibly could about the build. There's some room left to optimize what we cache and how we cache it so that we can reuse it across more jobs more efficiently. But that's about as optimized as build can get from JVM Arg perspective today, I think. Any questions?
Hey, Jason, awesome presentation. A lot of homework for us to do on some things. So let me ask you this: Does I think lately on Android Studio, I'm talking about just the local builds and things like that, and how we can improve. We have like one project, client project, where we have like 11 modules, and I think those guys run into some. It takes a little bit longer to even build locally, and I noticed on Android Studio lately there's been the what is it, build analyzer or something like that. Is it, did you guys monitor some of it on there, or like to see if it is even telling you something tangible? I've not looked into it much.
No. What I looked at was Gradle Enterprise build scans, Gradle validation scripts, a bunch of process monitoring, the JVM, Metaspace and code cache output. There's a bunch of other things that I'd like to look into. For instance, Gradle Profiler doesn't work with configuration cache, but it has a really, really nice visualization that you can dump into Chrome DevTools for looking at Gradle tasks and correlating it with memory usage over time and other things. Jake Wharton has a really good blog post from like 2018 about it. It works, and actually, so I have a GitHub repo that's public. I just called it Android CI, and it's got basically all my latest thoughts about how to do all of this and a proof of concept implementation. So if you're curious, you can check it out. Also, just for giggles, I just switched it back to Gradle build cache because I wanted to show that this method is faster, even for the smallest project ever, of just like if you make a Hello World Android Studio project. It's not. Um, Slower by about 20 seconds. But I know that once you do scale beyond like a Hello World single activity with nothing inside of it, you will cross a point. I just don't know what that point is today. I also know that there's some room for efficiency on like what we cache. Like for instance, transforms directory doesn't need to be cached if you can pre-build your Gradle convention plugin directory separate from the cache that's going to be used for configuration cache. So there's some things that can be better. Yeah.
And follow up, like, so we are slowly migrating to using GitHub Actions. Are there like any of plugins on the marketplace that we could try, which would kind of spit out a little report? So as we are making some of these changes, we could kind of see that you know of.
Um, so not a Gradle act. I mean, not a GitHub action that I'm aware of, but there are some pretty neat Gradle plugins that would spit out useful information and reports. For instance, Gradle Doctor, that is helpful. Its recommendation about parallel, I think, is now questionable because I know a couple of organizations that have said that G1GC is just faster, even without like incredible amounts of tuning. And there's also other things like just sort dependencies and other things. There's a ton of there's a really good ecosystem for Gradle plugins for builds and CI that's started coming around. Also the Slack Gradle plugin is pretty awesome. GitHub Actions is not GitHub in general has been slow with the Gradle ecosystem. They only got Dependabot working again this year after like a year and a half hiatus um, because they didn't support the Gradle version catalog.
Oh, yeah. And we
But
started using that on a few of our projects. So it's really nice. Yeah.
yeah, version catalog super nice. I love it. I'm using it in this proof of concept with Dependabot. All works great. Um, yeah.
Awesome.
Hopefully we can like as a community write some GitHub actions or like contribute them to the Gradle org. I don't know. It's a little bit Wild West. I am talking with Dan, who's the owner and maintainer of the official Gradle build action, so that we can get the environment variable configuration cache thing into the official action, and then get that working and just running for everybody's projects. So that's the next step or hope, I think.
You had a question in the room too.
Sure.
Hi, is Sayed here?
The microphone's echoing a lot.
Let me get it onto the other mic. Okay. Hi, so the question is about let me get closer. Hi. So the question is about running Gradle scripts from outside Android Studio versus using Android build. Those are not really related to the wonderful work you share. So how do you see, if any, difference running outside ID, how it impacts the speed of build?
So in terms
versus from IDE.
So in terms of outside IDE versus inside IDE, the main thing that I see is just Gradle sync time. That the IDE does indexing of your code, and then it says, I'm going to sync now. And then after the sync completes, then it does indexing again. It's like, okay, like I've been ready to build, and I went and got my coffee and I came back and you're still here. So then I open up terminal and I just say build, and I have like node watch that build. And I'm like, I'm using a build system to watch a build system to build my app, and it feels crazy. And then if you are React Native, it's even wilder. I with configuration cache and with build cache, I got to a pretty good place where it was like I would make a change and then I would wait 6 or 16 seconds for it to update. That said, when you like launch your ID at the beginning of the day, yeah, Gradle sync because you changed a branch or you changed a single white space character in a Gradle build file. That's kind of inevitable with that. A good way to mitigate it is writing Gradle convention plugins to make where you make changes more centralized in terms of like managing your dependencies, and Slack Gradle plugin demonstrated this, and I didn't get it at all for like 6 months. And Nicholas Ansman, when he joined Hinge, he really pushed for this, and eventually I saw the benefit, because when we wanted to change things across the entire code base, we could make drastic changes without rewriting individual Gradle build scripts in every single module. That doesn't save you anything with Gradle's sync time whatsoever. Doesn't solve that problem. What could save that is a project that Airbnb has been working on. It's very high investiture, but it's promising that they got it working at all. They gave a talk about it at DroidCon New York, and it's called AAR syncing. What they do is they generate AAR artifacts, and then instead of doing syncing against your actual project, they under the hood switch out what you're looking at, and they have Android Studio sync against the AAR artifacts, and they're constantly updating and publishing those as people commit changes and make builds. That's a lot of infrastructure and maintenance. I can't imagine anyone smaller than Airbnb even attempting it. I'm
just thinking, though, sorry, let me make sure that there's no reverb weird stuff. But from my perspective, that is such an enormous overhead, and it's basically the same thing that iOS does with a lot of weird SPM stuff. So they've basically built another version of SPM,
It tracks.
but with a compression on it.
Yeah, but it is faster. They got their sync times from 6 minutes down to 3, and then they were like, how do we get it smaller than that with like thousands of modules? And the answer is don't sync all the modules and then use AR effects because they sync faster, and then it's like 30 seconds.
All they're doing is paying the tax of running absolutely everything in a monolith
Yeah,
instead of splitting it into separate libraries with a deployment process that would basically do it anyway.
yeah.
So like there's no advantage of this versus you have the code bases split and you run it on an artifactory and it just runs periodically.
Yeah, they've basically done all of that for me.
I mean, it sounds cool.
And it's cool, and I'm glad it works, because the idea that that could be part of the build system eventually, so it could allow large projects to just scale like that if you want to and not have to think about it. That's also how I think about the JVM Args, is like some of the stuff that I did, Gradle could just look at your project and be like, oh, you know what? There's hundreds of modules here. You know what? The reserved co-cache size should not be 32 megabytes. It should be like 128 or 256. Like it should be bigger than what the JVM default is, because that's silly. Because we all know, and Gradle knows, in its own code, that like it will use more. So like this could be better. JVM arg tuning shouldn't require someone spending 6 months to research all of this. What we should do with this now is turn around and automate it and be like, okay, that's a solved problem for everyone. People should not walk away from this talk copy pasting this and then putting it in their build. What we should do is organize the effort into open source and make it better for everybody, and then move on.
The thing I'm trying to get people to do is actually build all of their things with custom plugins and use the build extensions. It's great. I just made my own, another one today for Spotless. And I wrote it once and it applies everywhere. Like, I just kind of wonder when that's going to become a more popular thing or more standardized, honestly.
Spotless is nice. My only caveat is that it's not configuration cache compliant, but it's hard.
It isn't, but if you attach it to its own thing that executes exclusively at the end of stuff, right? Like I only have it analyzing
it's fine.
non-Kotlin code, right?
Yeah, and it's fine to have in your build. I think if you're like really optimizing for performance, you like grab the binaries of KT format or whatever and just like run them yourself. But that's seconds. It's seconds that we're saving here. So it's like, why bother? If it's seconds for like hundreds of developers across millions of builds, then that makes sense. But like when I'm
At
building,
that point, you run everything in the CLI, right?
yeah. Or you do what Uber did, and they have like supercomputers that like build the code base constantly, so that when you're in an airplane flying across the world, you don't have to build it or worry about the network latency.